Hi, and welcome to H1.2 Angular Velocity and Angular Acceleration. In this lesson, students will be able to calculate and describe angular velocity, and students will be able to calculate and describe angular acceleration. I'm putting them both in the same lesson here because we've already talked about velocity and acceleration. We're just doing it in a rotational frame of reference right now. So as a little add-in to this, you might have noticed driving in a car, there's like this little thing over here. It says RPM. What the heck does RPM mean? Do you know? Think about it. Think about it. It stands for revolutions per minute. Revolutions per minute. And it's used to measure how fast any machine is operating at a given time. In cars, RPM measures how many times the engine's crankshaft makes one full rotation every minute, and along with it, how many times each piston goes up and down in its cylinder. This is a nice GIF here that shows the pistons moving the crankshaft, and there's like combustions that are happening here that causes the piston to move. In the extension folder, there's a website that shows you how a car engine works. Pretty cool, interesting read. So anyway, this dial measures the angular speed of an engine's crankshaft. Take a look at those units, revolutions per minute. That's almost like a meter per minute or meter per second, right? A distance in a certain amount of time, but this is the angular distance, the revolution, how many revolutions per minute. And notice this is times 1,000, right? So this would be 4,000 revolutions every minute. So every minute you make 4,000 turns of the crankshaft if it was at that dial. And then don't forget, this is also showing the linear speed of the car itself. It looks like this is in miles per hour, and they have the kilometers per hour there as well. So interesting thing, we're talking about revolutions per minute. How fast are you spinning? It's a measure of how fast something is spinning. How many revolutions per minute? All right, so continuing with our rotational kinematics. Yesterday we talked about, okay, displacement, but we're going to use angle, an angle around a turn, like a circle. That's your angular displacement. And then how fast are you going to change your displacement? That's your angular velocity. This Greek letter is the lowercase omega. All right, it's not a W. Yeah, so you use omega to represent the angular velocity. And we'll also talk about the angular acceleration. This is alpha. This is theta. We know that. Okay, let's get into it. So angular velocity, denoted by the Greek letter omega, is the rate of change of angular displacement with respect to time. Angular velocity is a vector quantity, and if you're moving clockwise, you have a negative direction, and if you have counterclockwise, we call that the positive direction. The units, what do you think a unit for angular velocity might be? Well, we just said revolutions per minute, right? RPM, that's a pretty common one. But for this class, they'll either be degrees per second, you might see it as revolutions per second, but the SI unit, what do you think? Radians per second, rads per second. That's typically what we'll use. You couldn't get away with using these in your kinematic equations as long as all the units for your angular displacement are also in degrees or revolutions. Those all have to agree. When in doubt, just put everything in radians and then you'll be good to go. The formula. What do you think the formula for angular velocity might look like? Pause the video. Come on, pause it and think about it. You could probably figure it out on your own. It's the rate of change of angular displacement with respect to time. So it's almost like the V is equal to delta D over T formula. But we have the change in angular displacement. How much of an angle did you go through in 1 second? That's what we'll do, right? How many radians per second? So where is this angular velocity formula on your reference table? It's located on that infamous page 7 that I created, and it's right over here. All right, the average angular velocity is equal to the change in displacement over time. Don't forget that, again, the units must agree with these, meaning if they're all in degrees, everything has to be degrees per second squared. But for these formulas down here, everything has to be in radians, radians per second squared. So let's do an example. It says, what is the angular velocity of the hour hand, minute hand, and second hand of a 12-hour clock? Yesterday we did the angular displacement in a 24-hour period, how many rotations in a 24-hour period pretty much. But now we're just talking about what is the angular velocity? Are these angular velocities positive or negative? And predict which has the greatest angular velocity. So pause the video and see if you can answer these two questions right away. All right, so if we're talking about a clockwise movement, clockwise is negative. So these angular velocities, we're going to call them negative. And which has the greatest angular velocity? Which one is like moving the fastest? What do you think? I'm going to predict the second hand is going to be the greatest angular velocity. Let's do some calculations. So for the hour hand, what is your rotate? Let's say you can make one rotation, so one complete revolution, one revolution. Why don't we call that 2 pi radians? We'll use radians. And then how long, how much time does it take for you to do one revolution for the hour hand? Think about it. It comes back to here 12 hours later. So this is 12 hours. Should we put it in terms of seconds? We should probably do rads per second. So 12 hours. Don't forget, this is the dimensional analysis thing. So hours, and then you could go into minutes. So there are 60 minutes in 1 hour. And then you could also do, okay, so the hours are going to cancel. The minutes should be on the opposite side, so they cancel. So seconds here, 60 seconds in 1 minute. So you just do 12 times 60 times 60. Or 12 times 3,600, because there's 3,600 seconds in every hour. So we have 43,200 seconds. That's equal to 12 hours, right? It's a 12-hour period for the hour hand to go around once. So then what would the angular velocity be? The angular velocity is equal to the change in the angular displacement with respect to time. So this angular velocity, and this is technically the average angular velocity, is 2 pi divided by 43,200, and you get about 1.45 times 10 to the negative 4. And what are the units for angular velocity? Radians per second. So that's how we write that. Now, note, I did forget something here. So we are moving clockwise, which means our angular displacement is negative, which means we have a negative angular velocity there. Okay, let's do the minute hand. So for the minute hand, again, we'll think about, okay, how long does it take the minute hand to go around once, meaning an angular displacement of 1 revolution or 2 pi radians, and you're going around clockwise, so we'll make that negative. All right, so what is the time it takes for the minute hand to go around once? You might say 1 hour, which if we did the conversion, gives you 3,600 seconds for the minute hand to go all the way around once. So again, your angular velocity is your change in your angular displacement with respect to time. Your angular velocity is 2 pi radians in 3,600 seconds, which gives you 1.75 times 10 to the negative 3 radians per second. So far, the minute hand has a larger magnitude than the hour hand does. See how that's a smaller decimal? So the hour hand is moving slower than the minute hand. How fast is the second hand traveling? So for the second hand, again, we're going around once. How long does it take the second hand to go around once? Hopefully you say 1 minute, which if we do the conversion, gives us 60 seconds. So again, we have a angular displacement, we have a time, we'll use the formula. And as predicted, that is the largest value for the magnitude of the angular velocity. And as anybody could have predicted, I forgot the negative sign over here. So you might be screaming at your screen, Mr. Nangle, this is supposed to be negative because it's clockwise. Yes, you are right. Very good. Okay, great. All right. Now we're ready for angular acceleration, denoted by the Greek letter alpha. Okay, not an A, this is an alpha. The rate of change of angular velocity with respect to time, and angular acceleration is also a vector quantity. And luckily it's the same convention where clockwise is negative and counterclockwise is positive. So what do you think the units for angular acceleration might be? Pause the video and think about it. You should know it. All right. There's 3 different options. You could have a degree per second squared, because it's acceleration, right? How many degrees per second are you changing per second? Or you could have a revolutions per second squared, but the SI base unit, hopefully you predicted, is a radian per second squared. How many radians per second are you changing your angular velocity every second? Okay, so the formula, again, pause the video, try to write down the formula using those Greek letters. What do you think the formula looks like? I'm telling you, pause the video, try it out on your own first, because if I just show it to you, you're not really thinking. See if you could figure it out. Did you write this down? Alpha is equal to your change in angular velocity, or delta omega, divided by time. Hopefully, again, this looks familiar. We can compare it to the linear acceleration formula, where it's the change in velocity over time. All right, so very similar idea here. And where is it located in the reference table? On page 7, right over here. Okay, so very similar location to even page 6 of the reference table, where you had the average velocity and then the average acceleration. All right, so let's talk about the direction of these vectors. We've been saying that clockwise is negative and counterclockwise is positive, but what we haven't really been saying is, well, up until this point, vectors were described with an arrow, you know, and we have this curvy arrow, I guess, if it's going counterclockwise like that, and we could call it positive. But it's not a true arrow like we've been seeing with vectors. So to get that arrow there, we have this convention where we use the right-hand rule, and then this is the direction of the angular velocity pointed along the axis of rotation. And it points in the direction that your thumb points when you do the right-hand rule correctly. So here's the rule. And it's important, you have to use your right hand. You cannot use your left hand for this because it'll point in the opposite direction. The convention is for the right hand. So you grasp the axis of rotation with your right hand so that your fingers circle the axis in the same sense as the rotation. So this is the sense of rotation of the wheel, and you're going to curl your fingers around. See how they're pointing in the same direction? You're curling your fingers around here, okay, in the same direction as the sense of rotation of the object. That forces your thumb to point in a certain direction. It says your extended thumb points along the axis in the direction of the angular velocity vector. And now we have a direction of the vector using our good old-fashioned arrows that we use to describe vectors. It's in the direction of your thumb. So that's for the angular velocity, which is a vector. And we said angular acceleration, that's also a vector. So think about what we know about the direction of the velocity and the acceleration. It says the angular acceleration vector also points along the axis of rotation. And when the angular velocity is increasing, that means that your angular acceleration is pointed in the same direction. All right, so you could have this like alpha thing. Okay, the angular acceleration's moving with the angular velocity, causing it to increase. We saw that when we had an object moving to the right with a certain velocity, and if you were accelerating to the right, that means you were speeding up. But what happens if your acceleration was in the opposite direction? In this case, negative. That means that you would be slowing down. So the same thing holds true. If your angular velocity is pointed this way, but your angular acceleration is pointing the opposite way, that means that your angular velocity is decreasing. So it says when the angular velocity is decreasing, your angular acceleration is pointing in the opposite direction. So this is the wheel slowing down, something's causing it to slow down, or maybe something is causing it to speed up. And if the angular acceleration is 0, it's a constant angular velocity. So let's do an example with angular velocity. It says a jet awaiting clearance for takeoff is momentarily stopped on the runway. As seen from the front of one engine, the fan blades are rotating with an angular velocity of negative 110 radians per second, where the negative sign indicates a clockwise rotation. So they're moving this way, clockwise. As the plane takes off, the angular velocity of the blades gets larger. It reaches negative 330, so it's speeding up in a time of 14 seconds. Find the angular acceleration, both magnitude and direction, of the rotating blades. So now we get to do the classic guess method stuff, right? So the initial angular velocity, we'll call that omega I, is equal to negative 110 radians per second. And if you're confused, like angular velocity, is that omega? I'm not really sure. One thing I always look for is the units. So if I see a rad per second, I know that's some kind of angular velocity and not an angular acceleration, because that would have been rads per second squared. So same as always, we're looking at the units, reading the problem carefully. And then it says it reaches a new speed of negative 330 radians per second. So we'll call that omega f is equal to negative 330 rads per second in a time of 14 seconds. Hopefully by writing the guess method out like this, it is almost muscle memory, and you know how to do this. It says find the angular acceleration, both magnitude and direction. So you can make your Greek letter alpha like that. That's what we're looking for. So givens, unknown, we'll write the equation. So alpha, and I realized I didn't really show how to draw these. I just kind of make like a little fish. It just doesn't have to, I'm not great at it. Okay, alpha is equal to, and then it's not, I don't want to see that. Okay, it's not a W. Make it like kind of curly with like a little loop maybe in the middle. It doesn't have to be a very pronounced loop. Like it doesn't have to be, whoa, that's kind of crazy. Uh, Something like that. So you want the change in your angular velocity with respect to time. We didn't actually expand this out yet, but you should know how to do it already. It's just omega f minus omega I. That's your change in your velocity, final minus initial. But now it's a change in angular velocity. So this is our equation. We substitute in the values. being careful with our negative sign. So omega F is negative 330 minus negative 110 divided by 14. And then you get negative 15.7. And then what are the units for angular acceleration? It's going to be a radian per second squared, just like that, okay, right? Because this is a rad per second, this is a rad per second, this is a second, so you get a radian per second divided by seconds, which turns into a radian per second squared. Fun stuff, all right? And then take note, this is a negative direction, which makes sense because you want the angular acceleration to be in the same direction as your initial angular velocity if you were to speed it up, like we talked about on the previous slide, right? Since the angular acceleration is pointing in the same direction, you're going to get a larger magnitude for your angular velocity. So you could just, there's like a couple conceptual questions here. You could pause the video, read it, think about it, and then I'll go over it very briefly. So pause the video here. Number 1 says a pair of scissors is being used to cut a piece of paper in half. Does each blade of the scissors have the same angular velocity, both magnitude and direction, at a given instant? You might say, well, it's the same magnitude, but hopefully you can see that this blade's going to go this way, and this blade's going to go this way. The top blade is going counterclockwise, and the bottom blade is going clockwise. So they do not have the same direction. So they do not have the same angular velocity. So I would say no, even though the magnitude might be the same speed, angular speed, different angular velocity because it's a different direction. Number 2, an electric clock is hanging on the wall. As you are watching the second hand rotate, the clock's battery stops functioning and the second hand comes to a halt over a brief period of time. So it's like decelerating, it's slowing down. Which one of the following statements correctly describes the angular velocity and angular acceleration of the second hand as it slows down? So we know right off the bat, the omega and the alpha are in opposite directions because you're slowing down. There should be in opposite directions. So let's start with what direction is the second hand actually traveling in? The second hand is traveling clockwise. So that means that the direction of the velocity is negative. But if it's slowing down, that means that the angular acceleration must be in the opposite direction, and the opposite of negative is positive. So that's going to be choice C, where omega is negative and alpha is positive. In this case, it would be speeding up. In this case, it would be slowing down, but omega would be pointing counterclockwise, and that's not the direction that the second hand goes. And in this case, again, it would be speeding up because they're in the same direction. Anyway, that's about it. Thanks for watching and have a great day.